Question 19, then we just have to do a rearrangement of this equation to make E the subject. Well, first step, we need to obviously get rid of the square root, square both sides. Next step is to eliminate the fraction by multiplying by the denominator. Now, you're trying to make E the subject, and E appears in two places, so the correct protocol to deal with that is to get all the terms with an E in on one side, factorise the E out of those two terms. So we're going to deal with this plus 2E, I'm going to move that to the other side to make it minus 2E over here. So effectively we're subtracting 2E from both sides of the equation. Take it away from the left side, take it away from the right side, and then we can factorise to get E on its, to isolate E, and divide by the bracket at the end to get our answer. Okay, nice easy 3 marks. Or it might be 4 marks actually, but you know, that's pretty routine, that, nothing very exciting there. But it is considered, I think, to be a grade 8 question. Question 20, fairly standard upper and lower bounds question. It's worth noting that this is a context-free question. It's a purely abstract maths question. There's no Sandra has 3 apples or anything like that. So we don't need to do much interpretation here. We just need to understand the difference between significant figures and decimal places. And even then, frankly, it doesn't make any difference in this question. 3 has been rounded to 1 sig fig. So effectively, it's been rounded to the nearest integer in this case. So 2.5 to 3.5 would be the range. I like to set them out like this. So, I've done Z first, sorry. Let's look at Z. 1 decimal place, so 5.25 up to 5.35. With Y, has been rounded to 3 sig figs. Now look carefully here. There's the first significant figure, because it's the first non-zero digit. There's the second significant figure. And there's the third significant figure. It's just the third digit after the first one. So it's been rounded to that one there. And that's in the hundredths column, so it's been rounded to the nearest hundredth. And therefore, we need to go half a hundredth up and half a hundredth down. In other words, 5 thousandths up and 5 thousandths down. But you probably saw that coming anyway. And we've said that one already was 2.5 to 3.5. Now, looking at the expression, to maximise this, to find the upper bound of it, to maximise it, I think we need the biggest x, the biggest y, and the smallest possible z. In other words, the biggest x, the biggest y, and the smallest possible z. So just take those 3 values, substitute them in, and get your answer. Now, notice I haven't rounded the answer. I've left it with all of the numbers on the calculator display, because there's no indication in the question about what accuracy to give our final answer to, only what the kind of original values were rounded to. In reality, you wouldn't round, you'd probably round this to 10.3, 10.9, probably, just because the highest level of accuracy in the original figures is 3 sig figs, so you can't really go any higher than 3 sig figs in your answer. But for GCSE, just put all the numbers in the calculator display. Okay, here's the Venn diagram question 21. This requires you to understand, in sufficient depth, these odd expressions like this, but we can break those down. We'll come to that one in a moment. First, we have to find the number of elements in. Do you know what? Actually, let's rewind a couple of steps and just read the question carefully. Up here, 6, 3, 7, 5, 2, 9, 4, and 8 represent numbers of elements. Now, I don't like the wording, and they always use this wording. What they mean is those figures here represent how many elements there are in each region, not the numbers of elements. That's slightly ambiguous. If I gave you a 3 element and said, what's the number of this element, then that's ambiguous, isn't it? You don't know whether I'm asking you how many are there or what's the number on it. Well, if you ever see this, it means, it literally means how many there are. So there's 6 different elements here. We don't know what those elements are. They might be, letters or elements or like chemical elements. There could be absolutely anything, but there's 6 of them there. So find the number of elements in A union B complement. Well, what does A union B look like? There's A union B. The complement of that is everything that we didn't just shade in. So everything out here. Okay. So how many elements are there now in the shaded regions? Well, it's the 4 and the 8. So 12. Okay, straightforward. Let's clear a space. Right, now we go a bit more complicated, but it's only more complicated because there's an extra step. Just look at do the brackets first. A union C. Right, A union C, there it is. But then it's A union C complement. So do exactly what we did in the previous part and instead look at everything outside of A union C. And then we take that and next step, we're going to intersect that with B. Well, B is the whole of the B, sorry, just catching up. B is the whole of the B circle, not just the 7. B literally means the whole B circle. B is a circle. It's not, not that just that little bit with a 7 in. So we're intersecting the blue bit with the orange bit now. So thinking about this, we've got that shaded in orange, that shaded in blue, and intersecting is where we've shaded twice. So it is just the 7, turns out. That whole thing refers to the 7. Quite often people think that B alone is somehow 7, but no, you need actually more complicated expressions to isolate these kind of outside, this 8, this 6 and this 7. You need these complicated expressions for those. Okay, and then finally we have to shade the region that represents the set A union B intersection C. Same drill, let's shade in A union B, and then shade in C, and we're intersecting those again. So which bit have we shaded twice? Well, it's that nice little funny shape there. This question, went through this with a few of you in class. You've just got to, you might be able to hear some nice music in the background. That's because I'm in room 15. In order to answer this question, in order to calculate the area of the sector, we need the radius. You simply are not going to be able to do it without knowing OA or OB. So what information do we have where we can work that out? Well, there's nothing here that isn't on the diagram, so just cross that out. We don't care about that information, it's here. I don't know why they write it again. There's just no need. But always just check that there isn't any extra information there that you haven't got on. The 7.2 is the key. That's got nothing to do with the area really, not directly anyway. But it will help us work out the radius, because there's a link between this 75 and this 7.2. And there's a formula for arc length. You go, how much of the circle have you got? Well, we've got 75 360ths of the circle, and it's the circumference we're interested in. So 75 360ths of the circumference, 2 pi r. And we know that that equals 7.2. And if you rearrange that for r, you get about 5.5-ish. I'd save that number on my calculator display and just leave it there for the moment. And then we can look at the area. So we want 75 360ths of, this time, pi r squared, which is the area of the whole circle, but we're just having that fraction of it. And we know, substituting our value of r into that, use the exact value on your calculator display, just press square and then times that by pi, and then times that by 75 and divide it by 360, and you get your answer. Round it to 3 sig figs, because that's what it says in the question. Second last question, simultaneous equations. This is standard, you've done these hundreds of times, no excuses anymore, please. Here is the biggest mistake I see people doing. They go, If only the bottom equation had x squared and y squared in, then I could just solve this for x squared and y squared as if it's just a and b. So we square all of the different terms in the bottom equation. And when people do this, I face palm because it just doesn't work like that. It's not how maths works. It's certainly not how you've been taught to do these problems. Here's why that doesn't work. Imagine you start with a plus b equals c, just for 3 variables. Does it then follow that a squared plus b squared equals c squared? Well, if it did, then, well, we recognise this, don't we? This is Pythagoras. But if this line follows from this one, then it must also follow the other way round. We must be able to start with a squared plus b squared equals c squared, and from that derive the fact that a plus b equals c. Well, now, Pythagoras' theorem's been around for 4,500 years, and it would be rather sad if nobody had spotted that simplified to a plus b equals c. It just doesn't simplify. If you, for example, put 3 squared plus 4 squared equals 5 squared, which we know is a nice simple Pythagorean triple, is it true that 3 plus 4 equals 5? Clearly not. So the trick with this is instead to write y as the subject of the simple linear equation. Because when you do that, you can substitute that expression into the first one. So the first equation is x squared plus y squared equals 52. And now you've got one equation, one unknown, and you've done it properly. So correctly and carefully expand the square bracket. And you end up with a simplified quadratic. Now you can type that into your class whiz and get the answer straight out of that if you're careful and you know exactly what you're doing. But if we solve it the proper way, using the A, C and B method, two numbers that times together to give 60 and add to give minus 32, minus 30, minus 2, if you search for a moment. So we split up the middle term like that. So notice I've split the minus 32x is now minus 30x minus 2x. And if you look at that as two different parts, I always draw a wiggly line there in between. And you factorise each bit separately. So out of these two terms we can take out a factor of 5x. That gives us one of the brackets. And that bracket we're going to use for the second part as well. So how many x minus 6's is this? Well, it's... You realise after a little bit of thinking you need minus 2 to make that work, because minus 2 times x gives us minus 2x, and minus 2 times minus 6 gives us 12. And then you've done it, you just go 5x minus 2, and then x minus 6. That gives us x is 2/5 and x is 6. And don't forget we also need the y values. I'm going to write them straight into coordinates because we should give x and y values as coordinate pairs. So there's our x values, and if you're careful and work out by substitute, look, you've got a formula here for y. Y is equal to 8 subtract 2 lots of your x value. And if you do that on your calculator for those two x values, you get those answers there. Okay, this last question takes time to interpret. And don't be afraid of that. I know it's the last question in the paper. You might be running short on time. If you've been careful with your timing through the rest of the paper, you've got a few minutes to get your head around this. We're taking taking a bead at random out of box A, you're putting it into box B, and then you're at random taking a bead from whatever's here and putting it in C, and then you're taking a bead at random from here and putting it all the way back into A again. And what's the probability that box A's contents is unchanged at the end of all of that process? Now you might spot that the only way of doing that is if we take a black out of A and put a black back into A. Sorry, I've misinterpreted the question there. It's the probability that that nothing has changed in any of the boxes. So if we take, therefore, a black out of A and put it in B, then B has received an extra black one, so we're going to have to take another black one out of B to put it back in C, sorry, to put it into C. And then C's just received a black one it doesn't want, so we're going to have to take that black one out of there and put that back into A, and then everyone's happy again. Or all of that again with white counters instead of black. I've prepared this a little bit with a bit of space here. Tree diagram is really helpful here. It's actually, you can do this without a tree, but if you've got time near the end of the exam, it really helps to understand what's going on here. You've got you've got a black or white from A to B, you've got a black or white from B to C, and then you've got a black or white from C to A. So you've got a triple layer tree diagram. Now, put your BWs on, and then we need to start thinking about some probabilities. So from A to B, there's 3/9 black and 6/9 white. Don't simplify the probabilities because it can sometimes hide patterns. Now from B to C, don't forget there's now 10 counters in. We've taken a counter out of A and put it in B, so there's 10 in here now. And if that extra ones are black, then 4 of those 10 are black and 6 are white. But if instead the one that we put from A to B is white, then 3 of the ones in B will be black and 7 will be white. And then when we take one out of B and put it into C, sorry, that's what we've now done. We've now got an extra counter in C and it's either black or white. So this last bit of the tree diagram is C to A. It's either black or white or black or white or black or white or black or white, depending on what's happened before. Well, there are 10 counters in C, and again, if that extra one is black, then there are 4 black ones in there out of 10, and 6 white. If that extra one is white, then, which is this W here, then the probability of the next one is, I've copied that down there because it's exactly the same. If the extra one is black, then those are the probabilities. And if the extra one is white, here or here, then you get 3/10 black and 7/10 white, 3/10 black, 7/10 white.